Now we have the second lecture of section 2.5. Okay, we're going to prove this theorem. It's called theorem 2.521.1. Let S be a set of real numbers which is bounded above. Then S has a unique least upper bound or unique supremum. Okay, so there's a lot of things going on here. So what it says is if a set is bounded above, so number one, there exists a least upper bound. Number two, that upper bound is unique. So there are a lot of things need to be proved, so we need some lemma here. So the first lemma is this. All right, actually, it's number 2 in your homework problem on page 54. I'm doing it for you right now. So let S be a set of real numbers and suppose that A sub n is maybe A sub n, not it. A sub n is an upper bound of S for any n belong to their natural number. So prove that if the sequence A sub n converges to a number A, then that A has to be an upper bound as well. Okay? Meaning you have a sequence of upper bound A sub n. If it is, we form a sequence and the sequence converges. And that number, the destination of convergent value, A, has to be an upper bound as well. So let's do scratch work first, right? We're going to do a scratch by picture. What does that mean? Meaning you have a set S right here. If a bunch of A sub n, it converges to a number A. Okay? So that's the set. You said whatever it converges to has to be an upper bound, which is above all the S's. Okay? We're going to do the proof by contradiction. What does that mean? Well, we're going to assume the contrary. If A is not an upper bound, if not, okay? Meaning a bunch of A sub n converge to a number, A is right here. If A is not upper bound, meaning somebody from the set S right here is greater than A. We're going to show that this is going to cause a problem, okay? Cause a problem, cause a contradiction. All right, so remember, ANs are upper bound of S. What does that mean? So if a number converts to A sub n converges to A, eventually very close to A, all the A sub n's are upper bound. Use another number like A sub n's right here. Well, if A is not upper bound, our contradiction is going to happen this way, right? Then some S is greater than A. We're going to say, hey, if that's the case, some A sub n so close to A going to be less than equals to what? Less than this S. Not less than equals, strictly less than those S. Meaning those A sub n cannot be upper bound anymore. So that's the contradictions. Okay? So now I'm going straight into the proof right here. Say that again. What are we proving is there is a sequence of upper bound A sub n, all right, which is converged to the number A. We're going to show that, we're going to prove that A is also what? An upper bound. So here's a proof. All right. So obviously we're going to use the conversion, the fact that A sub n converges to A as a part of our proof. Okay. So we're going to use that. So we're going to say proof. So we will use proof by contradictions. Okay. So assume the contrary. So what's the contrary? The result is contrary, right? A is not an upper bound. of S. So what does that mean? I'm going to use a picture, right? A is not upper bound, meaning this red A, okay, is right here, will be somewhere in there such that the some element of S is greater than this A. Okay, that's the reason it's not an upper bound. Otherwise, if everybody is less than A, if everybody from S is less than A, then A is an upper bound. So we assume the contrary, say A is not upper bound. That is, so what does that imply? That is, there is an element, I'm going to call it S, which is from the set S, such that S is strictly greater than A. Okay? X is strictly greater than A. Remember, we want to use a convergence. At some point, a lot of A sub n is strictly close to what? Close to A. Okay? And those A sub n are upper bound. We're going to say, hey, if that's upper bound, A sub n is upper bound, what are they doing there that is less than equal to S or less than S? So what we're going to do is use the convergence property, right? So given epsilon equals to, let's do this, S minus A over 2, which is strictly greater than 0 because S is strictly greater than A. Okay? Well, because A sub n converges to point A, there exists an cap n such that for all little n greater than or equal to cap n, A sub n minus A less than or equals to, I'm just call it epsilon over 2. Epsilon, not epsilon over 2, epsilon. Okay, it's called epsilon. So what does that mean? That means A sub n minus A less than or equal to epsilon greater than or equal to negative epsilon. Or A sub n less than or equal to epsilon plus A greater than or equal to negative epsilon plus A. Okay, I'm not going to worry about this part because I'm going to show that at some point A sub n less than the number they shouldn't be less than. Okay, so I'm going to focus on the right hand side. Okay, so what does the right hand side tell me? A sub n less than or equal to epsilon plus A. However, epsilon is what? Epsilon is S minus A over 2 plus A. So that's equals to, I'm just do some arithmetic for you, 2A over 2. So S plus A over 2. Remember, what is S? A is less than. Go back to here. A is less than A. S, so that's less than, strictly less than, S plus S over 2, which is 2S over 2, as you guess, less than S. So what does this line mean? Okay, recall, A sub n is an upper bound of S, yet we show that A sub n strictly less than S for some S belong to the cap S. This is a contradiction. Where does the contradiction come from? Come from, remember, we assume what? The contrary, A is not a what? Upper bound by S. So we need to change that. Therefore, okay, therefore, A is in what? Upper bound of the set S. So what do we show? If A sub n is a sequence of what? If A sub n is a sequence of what? Of upper bound and converge to a number A, then that number has to be what? Has to be in an upper bound as well. So this is the end of second lecture of section 2.5.